Hey everyone, my name is Ethan Jones, and this is Lab 3 at Georgia Tech about black holes. So in this lab, we'll cover how to use orbital motion to calculate the mass of a black hole, and we'll find the velocity needed to go around the black hole in a spaceship without getting sucked in. So as a quick preview, we will use Newton's second law, and we'll use Newton's universal law of gravitation. So as a preview of the results, the black hole's mass was 1.0597 e to the 34th kilograms, and the spaceship's initial velocity was negative 5 e to the 7th, 2 e to the 6th, and 0 meters per second as a vector. So for the models, we use Newton's second law, where F net equals dp over dt, and this can be expanded, so F net parallel equals this, and F net perpendicular equals this, and F net equals F net parallel plus F net perpendicular. So Newton's universal law of gravitation is F equals g, big G, which is the constant of gravitation, times the mass of one object times the mass of the other, over the magnitude of the displacement squared. So the position update formula is final position equals initial position plus average velocity times delta t, and we use the velocity update formula where the final velocity equals the initial velocity plus F net over mass times delta t. So we use these because we are dealing with gravitational force and the position and velocities associated with it. We assume F net is the sum of only the gravitational forces because we are dealing with the objects in space. So for the system and surroundings, in part 1, the system is the black hole and the surroundings is the star. For part 2, the systems are the ship and the planet separately, and the surroundings for when the system is the ship is the black hole and the planet, and when the system is the planet, the surroundings are the black hole and the ship. So for the initial conditions, the mass of the star is 2 e to the 30th kilograms, and delta t equals 1 day or 86,400 seconds. So for the first part, we'll calculate the mass of a black hole. So here's the code. So I uploaded the code that was given to me by the professor, and then I changed these certain values. So for line 122, I set the mass of the star. For 125, I changed delta t to show seconds and a day. For 164 and 165, I computed momentum using mass times velocity. For 168 to 169, I subtracted final velocity and initial, and then I subtracted final momentum from initial momentum. So for 172, I did change in momentum over change in time. For 175, I did F net equals dp over dt. For 178, p hat is initial momentum over its magnitude, or norm of it, which is a function. For 179, I changed the magnitude over change in time, or I did change in magnitude over change in time. For 180, force parallel is change in magnitude over change in time times p hat. 183, I assigned this value to parallel force, and then for line 186, I subtracted parallel momentum from total change in momentum to get perpendicular momentum. For 189, Newton's second law says change momentum over change in time gives force, so this is the perpendicular force. For 193, I rearranged gravitational force formula to get the mass of the black hole. So I've got several masses from this, and then I found the average of them, and this average was 1.0597 e to the 34th kilograms. F net was 8.53858 e to the 28th newtons. F net parallel was 2.35368 e to the 28th newtons. P net perpendicular is 8.19599 e to the 20th newtons. So for part 2 of the lab, I found initial velocity needed to avoid getting sucked into the black hole. So for the code for this, I again used the code that was given to me by the professor, and I changed certain parts. So for line 31, I put the mass from part 1 in. For 79, I did vector displacement from BH to the planet, or the black hole to the planet. For line 80, I used the gravitational force formula. For 82 to 83, I repeated the same process for gravitational force on the planet by the ship. And then for 85, I added the forces for net force. For 93 and 94, I did the same thing, and 96 and 97, I did the same thing. So, and then for 99, I found F net by adding both of these. And then for 105, I used the velocity update formula, and for 106, I used the position update formula, and again 108, I used velocity update, and 109, I used position update. So I found the velocity needed is negative 5 e to the 7th, 2 e to the 6th, and 0 meters per second. And then I found this through guess and check, and this gets the ship very close to the black hole without getting sucked in. So possible sources of error in part 1 include finding the average mass, and what I did for this is I plugged all the values in MATLAB and I found the mean of them. And for part 2, another possible source of error is not letting the code run long enough. So what does it mean? According to Newton's second law, F net is equal to dp over dt, While they are related, dp over dt specifically focuses on how an object's momentum changes over time, while F net represents the total force acting on an object, which can cause changes in its motion. Their parallel and perpendicular components are also related in the same sense, and they equal each other. What if? While this could have been several different answers, I found an initial velocity of negative 9.3 e to the fifth and 8.426 e to the sixth 0 meters per second puts the spaceship in orbit. This was found by Gissencheck. So in conclusion, the black hole's mass was 1.0597 e to the 34th kilograms, and the spaceship's initial velocity to avoid getting sucked in was negative 5 e to the 7th, 2 to the 6th, and 0 meters per second. Thanks for watching.